Hello and welcome to another video on tolerance stackup. In this video, I'll be trying to explain the Monte Carlo method in tolerance stackup analysis. What exactly is it in a very simple manner with a very simple example at the very basic level. Of course, Monte Carlo method is actually a very simple methodology which is used across many applications including data science and prediction of certain events using randomness. So we will understand its application in tolerance stackup analysis over here with a very simple example. Let's say we have a block uh, and the dimension of that block is as shown 250 plus or minus 2. 250 mm plus or minus 2 mm is the specification. The dimension is 250 and tolerance is 2. This plus or minus 2 mm is basically the upper and lower limit within which the block can be manufactured. So the maximum value the block can have is 252, the minimum it can have is 248. So the plus or minus 2, the tolerances are the limits of manufacturing. Now, if we are considering that the probability of the manufacturer to manufacture the part at 248, which is the lower limit, and 252, which is the upper limit, and 250, which is nominal, is all same, then we have this uniform distribution. So this is a probability distribution of, let's say for example, if you manufacture 1000 parts, what is the probability of you getting a part which is having a specification of 248, which is the lower limit? So distribution says that you have the same probability of finding a part which is having a dimension at lower limit as same as having it as a nominal or the mean, which is 250. For simplicity's sake, let us consider that the manufacturing process which makes this block has a uniform distribution. It has an equal probability of manufacturing at the lower limits and upper limits as compared to its mean, which is the nominal 250. Now, what if we manufactured 1000 times this same block and measured the 1000 dimensions, corresponding dimensions for each part which has been manufactured? So according to this uniform distribution, if we are manufacturing 1000 parts, we will get the number of parts which are equal as measured between 248 and 252. So here is a uniform distribution graph. So the parts which are measured at 248 will be the same as parts which are measured at 252. So if they are divided into 5 buckets, then 200, 200, 200, 200 will be there for all of the values which have been measured. So 1000 parts which are manufactured as per this drawing will have this uniform distribution. Now if we want to simulate the manufacturing of this block 1000 times, we can do that using a spreadsheet by generating random numbers within the range of 248 to 252. So here are 1000 instances and I will be generating random numbers between 248 and 252, and when we are generating random numbers, we are generating them with a uniform distribution by default. So uniform distribution is considered as an assumption over here. Of course, we can consider a normal distribution also, that will make it more complex. So we will start with the most simplest form. So to generate random numbers between two limits, we will use the random between, bottom is 248 comma 252. So it has generated a random number. If you just drag this for the 1000 instances which we have, so you can see that it has generated random numbers between 248 and 252, which is basically simulating the manufacturing process. We are simulating the manufacturing process and checking the measurement of this dimension for 1000 parts. So that is what is being simulated over here. That is the meaning of the simulation in the Monte Carlo simulation. Now if we are plotting the distribution of the number of paths which have got a reading of 248 versus 249 versus 250 versus 251 versus 252, then the distribution will come out something like this as shown in the earlier slide. Of course, the variation, it will not be 200 exactly because the number of samples which you have taken is 1000, which is less. If we take 10,000, then it will match more or less closely to the same level. So you can see that it is showing a uniform distribution. The probability of a part being 248 is similar to a part being 252, which is same as part being 250. So this shows a uniform distribution when we are generating random numbers 1000 times. So generating random numbers within a given distribution is nothing but the Monte Carlo simulation. We are generating random numbers within a given distribution, within a given probability distribution. Now that probability distribution might vary. It can be a normal distribution or a Weibull distribution or a Rayleigh distribution. Based on those distributions, the random numbers will get generated, which is simulating the manufacturing process. So that's the core idea of Monte Carlo simulation. Now let us consider an assembly of 3 blocks with the same dimension. So the same block is piled up 3 times. What will be the distribution for this specification? Let's find that out. So for that, we need to manufacture, or we need to generate 3000 random numbers. 3000 parts are manufactured and 1000 assemblies are made, simulating that 3000 parts are manufactured and 1000 assemblies are made. What will be the distribution of the total width of the stack? Let's find that out. Let's find the distribution for that using the Monte Carlo method. That is generating 1000 random numbers 3 times, and then as we do normally for a tolerance stack up analysis, we add up. As in this case, we are adding up these specifications, this plus this plus this. But whatever the loop diagram is for any other tolerance stack up analysis, we need to add or subtract based on that. So we are generating 1000 assemblies with 3000 parts, that is 1000, 1000, 1000, and then adding up the 3 and getting another number, which is addition of all the 3 random numbers. So we are simulating the part manufacturing 1000 times, generating random numbers as per the uniform distribution. Very important, this is as per the uniform distribution, which is shown over here. And then we are repeating it 3 times and then summing up the 3 to get the assembly width. You get 1000 assembly width. So let's do this in Excel. We will get the idea as to what kind of distribution we get for this specification. Will it be a uniform distribution as shown over here, which is similar to the worst case analysis? In worst case analysis, when we do the worst case analysis tolerance stack up, we consider the probability of it being at the lowest end, which is 744. So basically in worst case analysis, the calculation would be 250 plus or minus 2. 250 plus 250 plus 250 is 750, and 2 plus 2 plus 2 is 6. So 750 plus or minus 6 will be the specification as per the worst case analysis. And as per worst case analysis, the probability of having a part at 744 will be same as having a part at 756. That is the 2 extreme limits calculated as per worst case scenario. But using Monte Carlo method, do we get this kind of distribution or not? Let's see that. That will help us differentiate between worst case analysis and Monte Carlo simulation. If you are liking this video and content like this on tolerance stackup, I have a free ebook on tolerance stackup analysis in which I have shared multiple examples, case studies, different concepts relating to tolerance stackup. It is totally free. The link is in the description below. So here is the Excel sheet showing the Monte Carlo simulation. So what I have done over here is that for block 1, I have created 1000 random numbers within a range of 248 to 252 and using the uniform distribution, and these are the random numbers for block 1. Similarly, I have done the same thing for block 2. So block 1, block 2, block 3, and I have created 3 sets of random numbers, 1000 each, and then I have added these 3 sets of random numbers to get the sum over here, which is the assembly width. This is the assembly width. So you can see random numbers are being generated within that, and the distribution over here changes. So once we generate the assembly width using these random numbers, I'm plotting these assembly widths into the graph shown over here. So these 1000 values of assembly widths are plotted over here. As you can see, the distribution of the assembly width is like this. It is close to a normal distribution. So what it says is that the probability of finding a part or an assembly which is having the total width at 750, which is shown over here at the center, is much higher as having the total width at 744 or 756, which means that it does not follow uniform distribution. If you are doing this simulation, and if you're generating random numbers for each of the blocks and then summing them up and finding the assembly width, you will get this distribution. So here is the summary of the Monte Carlo method. The first step is we are simulating the process, the manufacturing process for 1000 times or 10,000 times or even more. The more the number of times you do, the refinement you will get in the distribution. You're simulating the process and generating random numbers based on the capability of the process, which is nothing but the probability distribution of a process for that specification. So the random numbers are generated based on the probability distribution for that specification. What is the probability of that specification being at its lower limits versus what is the probability of that specification being at its upper limits versus the mean. So that is the probability distribution. Based on that, the random numbers are generated. Then the final specification to be calculated, which is nothing but the gap or the width. As we had seen earlier, the three blocks are coming together to form a width. So that specification is then calculated for the instance of the assembly for 1000 or 10,000 assemblies. So of course, the more the number of assemblies, the more refinement you will get in the final distribution. And then we are plotting that probability distribution for that spec. And we will observe that unlike worst case analysis, the final spec is a distribution and it is not two extreme numbers. In the case of worst case analysis, we consider them as having uniform distribution. The probability of it having the lowest value is the same as it having the highest value, which is the same as it having the mean value in worst case analysis. Whereas in Monte Carlo, we will get actual distribution of how will it be in the actual case when the parts are manufactured as per the process, considering we are generating random numbers. Important point is there should not be any bias in generating the random numbers. So the distribution which is set for the process should be accurate, which is simulating the process, and based on that the random numbers should be generated. And when the random numbers are being generated, there should not be any bias. This is very important. If there is any bias, then this Monte Carlo simulation will fail. So Monte Carlo simulation is basically a calculated risk for known processes. So basically what we are doing is we are simulating the process in real time by generating random numbers and see how the result turns out. That is what we are actually doing. But we are doing it using random numbers and using statistics of the process. Hence, we need to understand the process thoroughly for using the Monte Carlo method sufficiently to use it in an effective way. If we don't understand the process, if we do not have a proper distribution of the process, and if it is unbiased, if it is not biased, then only we can use the Monte Carlo method without any issues, without any problems. Or else we have to resort to the worst case analysis, which is a more conservative approach. So Monte Carlo method is not a conservative approach. It is a calculated risk, because at the end we know that some portion of the parts or assemblies are going to be at the extreme ends, while majority of them will be at the mean. You can understand the difference between worst case analysis and Monte Carlo analysis with this table. So the philosophy in worst case is that what is the absolute disaster scenario? We are only worried about what is the worst case possible. Whereas in Monte Carlo, what is actually going to happen on the shop floor is what we are actually simulating. So in worst case, we are only looking at the worst case scenario. Whereas in Monte Carlo, we want to simulate the process. The result, a single range. We are getting a single range in worst case analysis, whereas in Monte Carlo, we are getting a probability distribution. The approach is conservative in worst case, it is liberal in Monte Carlo. We are doing a calculated risk. The risk is that there will be 0% failure in worst case analysis. We are considering a 0% failure. Whereas in Monte Carlo analysis, there is a calculated risk. Example, 3 out of 1,000 might fail. So there is always a calculated risk with Monte Carlo analysis. In the example, for simplicity's sake, we considered the distribution to be uniform, but realistically, most probability distributions are normal distributions, especially in manufacturing. So if you consider a normal distribution, then the generation of random numbers should follow that normal distribution. So in the spreadsheet, in the Excel sheet, we need to generate random numbers as per the normal distribution and using mean and the standard deviation as the inputs. So when generating random numbers, we need to use mean and standard deviation as the inputs and generate the random numbers as per the normal distribution. And then rest we need to do similar to what we had done earlier. We need to sum up the values and then find out the total width of the blocks.